All right, so you ready to take a deep dive into scaling systems?
Absolutely. Always fascinating to see how the sausage is made, so to speak.
Right, and from the looks of this material, there's going to be a lot to unpack.
Definitely. We're talking about the difference between, a website that crashes when a few hundred people use it versus one that can seamlessly handle millions of users.
Yeah, it's like the difference between a neighborhood bakery and like a giant industrial bread factory.
Exactly. And the key principles and techniques that allow those bread factories of the internet to work, smoothly, even with huge demands, that's what we're going to explore.
So it seems like from our source material, scaling isn't just a one-time thing. It's like an ongoing process, right?
Yeah, absolutely. The material really emphasizes that it's iterative. It's a constant dance between, anticipating future growth, but also adapting to current demands.
So it's like building a house with an expandable foundation.
Perfect analogy.
Knowing you might add on more rooms or even a second story later.
Yeah, and one of the first things the source material dives into is keeping the web tier stateless.
Statelessness. Okay, break that down for me a bit.
So imagine you're at a busy airport and every check-in kiosk has access to all the passenger data. It doesn't matter which kiosk the passenger used before.
Okay, so it's like having a system where every customer service representative has access to your complete account history.
Yeah, exactly. It makes things way more efficient. And in the context of scaling systems, statelessness lets you add or remove servers without data consistency issues.
Gotcha. So we've got our stateless servers ready, but how do we distribute all the incoming traffic between them? The source material mentions load balancers.
Yeah, load balancers are essential for any system with heavy traffic. They're like traffic cops, directing cars to different lanes to avoid congestion.
So the cars are user requests and the lanes are our web servers.
Precisely. The source material gets into the different types of load balancing algorithms too, each with its pros and cons.
Interesting. So there's a whole science behind how those load balancers work. But what happens if a server crashes? Is the whole system done?
That's where redundancy comes in. It's like having backup servers ready to handle the traffic if one goes down.
Like a spare tire in your car.
Exactly. You might not need it every day, but when you do, you're sure glad you have it.
Okay, so we've got load balancers, redundancy, but how do we speed things up for users? The source material talks a lot about caching.
Yeah, caching is key for high-performance systems. They use this analogy of a read-through cache in the material. It's pretty good. Imagine you have a library with millions of books, but you keep the most popular ones on a small shelf near the entrance.
So instead of searching the entire library every time, they can grab it from the shelf.
Exactly. And in a web system, the cache stores frequently accessed data in a place that's much faster to access than the main database.
So if I visit a website and look at a product page, that info might be stored in a cache, and the next person who looks at it can get it from there instead of the database.
Right, and that not only makes things faster, but it reduces the load on the database so it can handle other requests.
Brilliant. But what about dynamic content, like, personalized recommendations? Can that stuff be cached?
Traditionally, caching was mainly used for static content like images and videos, but the source material talks about dynamic content caching, which is really interesting.
Dynamic content caching. So what, like caching personalized content based on user preferences?
Yeah, exactly. It's a powerful technique for sure, especially for systems with a lot of personalized content.
This is starting to make sense. We've got our stateless servers, load balancers, redundancy, and caching. What about the database, though? How do you scale a database with millions of users constantly reading and writing?
That's the big question. The source material talks about two main approaches, vertical scaling and horizontal scaling. Vertical scaling is like upgrading your computer with more RAM and a faster processor.
So trying to cram more people into a small car.
Right. Eventually, you just need a bigger vehicle, and that's where horizontal scaling comes in. They call it sharding.
Sharding, right? I've heard that term. Remind me how that works again?
It's like dividing a pizza into smaller slices. Each slice can be handled independently, and you can add or remove slices as you need.
So you break up the database into smaller pieces and put them on multiple servers.
Precisely. And each piece contains a subset of the data based on a certain key. So you could shard a user database by their last name, for example. All the AFs go on one shard, GLs on another, and so on.
Ah, I see. So it's like organizing a library by genre or author.
Exactly. That lets you scale your database as your data grows. But there are some challenges, choosing the right sharding key, making sure the data is consistent across the shards.
Got it. So sharding's powerful, but it's not a magic bullet. Now, what about times when you need to do things that a traditional relational database isn't good at?
That's where NoSQL databases come in. They're great for handling large amounts of unstructured data, and they're more scalable and fault tolerant than the traditional relational databases.
It's like using the right tool for the job.
Exactly. And actually, the source material advocates for a hybrid approach using SQL and NoSQL databases to play to each one's strengths.
Okay, that makes a lot of sense. So we've got all these different parts of our system. How do they communicate with each other without creating bottlenecks? The source material mentions message queues.
Yeah, message queues are essential. Think of them like intermediaries handling communication between different parts of the system. Like if you have a system that processes orders, when a user places an order, instead of directly triggering all the next steps, the message queue acts as a buffer.
So it's like having a dedicated messenger service, delivering messages between different departments.
Exactly. And that lets different parts of the system operate independently and asynchronously without blocking each other.
Gotcha. Now this brings us to another concept. Consistent hatching. Sounds pretty technical.
It is, but it's also a very elegant solution when you're distributing data across multiple servers. It ensures that when you add or remove a server, only a small portion of the data needs to be moved around.
So it's like a self-organizing filing system that automatically adjusts when you add more cabinets.
Exactly. And consistent hashing not only helps with efficiency, but it also helps a lot when a specific piece of data gets a ton of traffic.
So it's like having multiple entrances to a stadium so everyone's not trying to go through a single gate.
Precisely. It helps distribute that load evenly and keeps things running smoothly, even with traffic spikes.
This is all fascinating. We've covered a lot, but I feel like we're just getting started. What else is there to consider when building systems at this scale?
There's always more to learn, of course. The source material emphasizes monitoring and automation tools and the need to design for future growth right from the start. We'll get into those more in part 2 of this deep dive.
That sounds great. This has already given me a whole new perspective on how these systems work. Let's take a break and come back for more fascinating insights in part 2.
Looking forward to it. So welcome back to our deep dive on scaling systems. Last time we talked about some of the fundamental building blocks, stateless servers, load balancers, things like that. But as systems grow, there are some more nuanced challenges that come up.
Yeah, I'm really curious to hear about those. What kinds of things are we talking about?
Well, the source material highlights a couple of things that are often overlooked but become super important at scale: unique ID generation and URL shortening.
Unique ID generations. I mean, can't you just use a simple counter?
For small systems, yeah. But when you have multiple servers generating IDs at the same time, things get tricky. You need to make sure each ID is unique across the entire system without any slowdowns or conflicts.
Ah, so it's like having multiple ticket booths at a concert, each printing tickets with the same numbering sequence.
Exactly. And that's where techniques like the Twitter Snowflake approach come in.
Twitter Snowflake, huh? That sounds interesting. What's the idea behind that?
Basically, you break the ID down into segments that guarantee uniqueness and scalability. Instead of one central counter, it uses a combination of things like timestamps, machine IDs, and sequence numbers.
Okay, I'm following. Timestamp makes sense, and the machine ID is distinguish IDs from different servers. What's the sequence number for?
That's to handle cases where multiple IDs are generated on the same machine in the same millisecond. It's like a tiebreaker, ensures that even those IDs are unique.
Pretty clever. Problem solved for ID generation at scale.
Pretty much. There are other approaches, but the Twitter Snowflake method is a popular choice. Now, let's talk about URL shortening. Seems like a pretty simple concept, right? You take a long URL and make it short.
Yeah, what's the big deal with that at scale?
Well, when you're talking about billions of shortened URLs, you need to worry about things like collisions, how much storage space you're using, and how quickly those shortened URLs can redirect back to the original ones.
Collisions. You mean two long URLs ending up with the same shortened URL?
Exactly, and that's why choosing the right hashing algorithm and collision handling is so important. The source material goes through a couple of different approaches to this.
So what are the ways to handle URL shortening when things get really big?
One way is to use hash functions like MD5 or SHA1, but these can sometimes produce collisions where two different long URLs end up with the same hash.
So it's like trying to put 1,000 unique keys on a keychain with only 100 slots. Some keys will end up in the same slot.
Right. One way to handle that is to add a counter to the hash value. But that can get complicated as the system grows, leading to longer shortened URLs and slower lookups.
Okay, so what's the other option?
Another approach is to use base conversion. You generate a unique ID and convert it to a different base, like base 62, which uses numbers, uppercase and lowercase letters.
Base conversion. So it's like translating a number into a different language.
Exactly. This ensures each ID has a unique representation, and because base 62 has more characters than the decimal system, you can pack more information into a shorter URL.
That's smart. So we've got our shortened URL. Now, how do we redirect users back to the original one?
Right. Well, the source material really stresses the importance of using HTTP redirects, specifically 301 or 302 redirects.
And which one you choose depends on whether you want to be more efficient or if you want to collect data, right?
Yeah. A 301 redirect is more efficient because the browser caches the redirect and goes straight to the target URL next time. But a 302 redirect lets you track things like click-through rates, which can be useful for analytics.
Gotcha. So the user clicks the shortened URL, the server redirects, and the browser takes them to the original. But how does the server know which long URL goes with the shortened one? Does it store a huge table in memory?
For small systems, maybe, but for massive amounts of URLs, you need a better solution.
I'm guessing the database comes back into play here.
Yep, most real-world URL shorteners use a relational database to store the mappings between shortened and long URLs, and they use techniques like indexing and sharding for fast lookups.
It's wild to see how all these concepts come together for something as seemingly simple as URL shortening.
It is, and as we move on to more complex things like web crawlers, news feeds, and chat systems, you'll see these same fundamental concepts keep coming up.
Sounds like a good place to pick up next time I'm ready to dive into some of those more complex systems.
Yeah, let's do it.
Okay, so ready to jump back into our deep dive on scaling systems. We've covered a lot, but I'm excited to hear what else is out there.
Well, how about we tackle a feature that's pretty much taken over the internet? News feeds, those never-ending streams of updates and photos and articles that keep us glued to our screens.
Yeah, news feeds seems pretty straightforward. People post things, their followers see those posts, but I have a feeling there's way more to it than that, especially at scale.
You're right, it's way more complex than it looks. The source material really gets into how these personalized streams of content work. We're talking real-time updates, efficient data retrieval, and personalized ranking algorithms, all at a massive scale.
So it's not just about showing posts in chronological order. There's a system that decides what posts users see and in what order.
Exactly. The material breaks it down into two main flows, feed publishing and newsfeed building. Let's start with feed publishing. What happens when someone creates a new post?
Okay, walk me through it.
So imagine a user shares a picture of their new puppy. That picture needs to be stored and then sent out to all their followers. This involves multiple databases, caches, maybe even message queues all working together.
So it's not just saving a photo to a server. It triggers a whole chain reaction.
Right, and there's this thing called the fan-out service that plays a key role.
Fan-out service. Okay, what's that?
It's basically a delivery service for newsfeed updates. It gets the list of a user's followers, filters them based on privacy settings and all that, then pushes the new post ID to each follower's newsfeed cache.
So it's like a super efficient mailroom sorting through all the incoming mail.
Great analogy, and it all happens incredibly fast, practically in real time.
That makes sense. But what about when a user opens their newsfeed? How does it decide which post to show first?
That's where ranking algorithms come in. They look at all sorts of factors to create a personalized feed.
Like what kind of factors?
Recency of posts, the user's relationship with the poster, engagement the post has gotten like likes and comments, and maybe even the user's past behavior on the platform.
So it's more about what the system thinks the user will be most interested in, not just what's newest.
Exactly, and caching is really important here too, to keep everything fast.
It's like having a well-organized pantry. The things you use most are right up front.
Right, and all of this has to work flawlessly with potentially billions of posts and millions of users.
How do they even manage that? How do you build a system like that that doesn't just collapse?
Well, sharding, replication, load balancing, all these things we talked about before, you have to distribute the data, the processing, the traffic, all across multiple servers.
Like a perfectly rehearsed orchestra, each section playing its part.
Love that analogy. It really captures the complexity of building something like this.
Okay, newsfeed. Got it. What other features are like this?
How about chat systems? Might seem simpler than news feeds, but reliably sending real-time messages to millions of users is a challenge.
Yeah, with chat, speed is everything. Can't have any delays or dropped messages.
Exactly. Low latency, real-time updates, maintaining all those connections, it's all super important. That's where WebSockets come in.
WebSockets, what are those?
Imagine them as dedicated phone lines between each user and the chat server. Instant two-way communication.
A direct connection, no waiting around for requests.
Right. Even a tiny delay would make the whole experience feel slow and clunky.
So that handles the real-time part, but what about online presence, chat history, group chats? Those have to be tricky at scale.
You bet. Managing online presence, that's about tracking who's active and letting their contacts know. It's a delicate balance between real-time updates and not overloading the system.
You don't want people to think you're offline when you're not, but you also don't want to constantly be pinging the server.
Exactly. And then there's storing chat history, potentially billions of messages that people want to access quickly.
So how do they manage that much data?
It comes down to the database and the data model. The source material looks at different approaches, using relational databases with sharding, NoSQL databases that are good for time series data.
So again, the right tool for the job.
Right. And then there are group chats, which add another layer of complexity, managing group membership, sending messages to everyone in the group, maybe features like threading or moderation.
Like organizing a massive conference call?
Exactly. And as the group gets bigger, scaling becomes even more crucial.
Okay, chat systems check. Before we wrap up, I have to ask about search autocomplete. You know when you start typing a search and it gives you suggestions?
Ah, yes, search autocomplete. Makes things so much easier, right?
It does. But I'm curious how it works behind the scenes.
Well, it uses a data structure called a trie, which is like a tree structure that's perfect for prefix-based searches.
So like a specialized dictionary for looking up words by their prefixes.
Exactly. And by caching those prefixes and limiting the length, you can get almost instant suggestions.
Like it can read your mind, knows what you're going to search for.
In a way, and to keep the suggestions relevant, it has to constantly gather and process search data, analyzing search logs, updating the trie structure, and that whole data pipeline needs to be scalable too.
It's like a team of librarians constantly updating the card catalog.
Great analogy. And, throughout all of this talk about building for scale, there's one thing we haven't mentioned directly: error handling.
Error handling. That sounds like something that's easy to forget about until something breaks.
It is. But when you're operating at the scale, failures are going to happen. The source material talks about anticipating those failures, having ways to detect and diagnose them, and knowing how to recover.
So it's like having a well-prepared emergency response team.
Exactly. Building these systems isn't just about writing code. It's about creating resilient systems that can handle problems when they inevitably arise.
This has been amazing. We've really gone deep on how these systems work. It makes you appreciate how much thought goes into building something that seems so simple on the surface.
I agree. It's really impressive what people can build.
So to everyone listening, think about the apps and websites you use every day. Can you picture all this happening behind the scenes? It's pretty mind-blowing, right? And here's something to think about. If you had to design a system for billions of users, what would be your biggest challenge? Let us know what you think. Thanks for joining us on this deep dive.